integral 0 to 1 upon 1 minus t cube minus t upon 1 minus t cube whole into dt. This equals integral from 0 to 1 dt upon 1 plus t square. By completing the square, you have integral 0 to 1 dt upon t plus half whole square plus 3 upon 4. Now this is a standard format integral which all of you must have done, of course. This equals 1 upon square root of 3 by 2 tan inverse t plus half upon square root of 3 by 2. Evaluate this integral over the limits 0 to 1 and you have 2 by root 3 into pi by 6 equal to pi by 3 root 3, which equals your right hand side. Let's move on to another question. If a is less than b, show that a real number c can be found in the open interval a comma b such that 3c square equals a square plus ab plus b square. How do you proceed in such a question? Clearly, there exists an inequality. You have to prove that a certain value lies within a certain domain. In such problems where you have to deal with inequalities, it's a good idea to see if your mean value theorems work. In this particular question, we'll try and apply the Lagrange's mean value theorem in the closed interval a comma b and see what we can do. Now focus on the fact that there exists a term 3c square and that there exists a square plus ab plus b square, both of which point to some cube of some function. We'll proceed from there on and we'll take an f of x which equals x cube in the open interval a comma b. Apply LMVT on this in the closed interval a comma b and we see that fx satisfies all the necessary conditions for this theorem to be applied. Now there exists a c in a comma b such that f prime of c, which is equal to 3c square, is definitely equal to b cube minus a cube upon b minus a, which equals a square plus ab plus b square, which is exactly what we've set out to prove. And where does c lie? Again, c exists in the open interval a comma b. Let's move on to another problem here. Evaluate integral of tan 5x into tan 3x into tan 2x dx. What is the most obvious fact here? The 5x equals 3x plus 2x. Let's try and simplify this integral in this fashion. For tan 5x, we have tan 5x equal to tan 3x plus tan 2x upon 1 minus tan 3x tan 2x. What does that give? That implies tan 5x tan 3x tan 2x equals tan 5x minus tan 3x minus tan 2x. Of course, you can generalize this particular formula to any a, b and a plus b as tan of a plus b into tan a into tan b equals tan of a plus b minus tan a minus tan b. So what do we have? We have our integral, the given integral equaling integral tan 5x minus tan 3x minus tan 2x whole dx, which is of course very easy to evaluate, and we go on towards the solution. Moving on to a question on vectors. A, B and C are three non-zero coplanar vectors. We have to prove that the given determinant equals 0. What is the most obvious thing about this problem? In the first line itself, it is stated that A, B and C are three non-zero coplanar vectors. So let us write C vector as a linear combination of A and B vectors. Let's say C vector equals x into A vector plus y into B vector. Now taking a dot product with A vector on both sides, we have C vector dot A vector equaling x into A dot A plus y into A dot B. Similarly, we have C dot B equal to x into A dot B plus y into B dot B. Now substitute these two into our determinant. What do you have? Take a look at the last column of the determinant. Now, take the second row, take the second column. Take a look. Now take a look at this determinant. Look at the last column of the determinant. Clearly, It seems to be a linear combination of some kind. Take the second column, multiply it by y, and subtract it from the third column. Now again, take the first column, multiply it by x, and subtract it by the third column again. What do we have? We have one entire row equaling 0, which implies that our determinant is equal to 0, which we set out to prove in the first place altogether. Let's move on to another question. We are required to evaluate the limit of a function as n tends to infinity, the function being greatest integer function of 1 square x plus greatest integer function of 2 square x plus and so on up till greatest integer function of n square x whole upon n cube. How do you deal with such a question? Clearly, we can't deal with the greatest integer function on its own, as evaluating the limit of the same is a very cumbersome job. So you write this out as the greatest integer function of x equals x minus the fractional part of x. So what do we have? We have 1 square x, the greatest integer function, equaling 1 square x minus fractional part of 1 square x, and so on, wherein a general term would be like greatest integer function of n square x equals n square x minus the fractional part of n square x. So the limit as n tends to infinity of this entire summation on grouping would look like limit as n tends to infinity 1 square x plus 2 square x plus and so on up till n square x minus the fractional parts of these very functions whole upon n cube. Now the first part is easy to evaluate. It comes out to be n into n plus 1 into 2n plus 1 upon 6n cube into x, and the second part is a summation of fractional parts of k square x upon n cube. So the fractional part of k square x is less than 1 for all k and all x's. So the summation from k equal to 1 to n of the fractional parts of k square x is always going to be less than n. So the limit as n tends to infinity, summation fractional parts of k square x whole upon n cube is less than equal to limit as n tends to infinity of n upon n cube. And clearly this term is greater than 0. You apply your Sandwich theorem and you have limit as n tends to infinity, the fractional part summation of k square x upon n cube equaling 0. So what are we left with? We are just left with our first term, which is limit as n tends to infinity n into n plus 1 into 2n plus 1 upon 6n cube whole into x, which comes out to be x upon 3.